So finally, let's answer the question, what is the efficiency of a Carnot engine? Even I was curious when I was studying this, when we can't have 100% efficiency, naturally if it's not allowing, so what is the best possible efficiency that we can have? So apparently this is the expression. Let's derive this out. So first thing is, we are dividing a Carnot cycle into 4 parts: isothermal, expansion, adiabatic, isothermal and adiabatic. And we are calling it as 1, 2, 3, 4 significant pressure volume values that we are dealing with. So one key thing that we need to make a note is, this is volume 1. Here we have volume 4, volume 2 and volume 3. To keep track of the temperature, I'm calling TH as T1. I'm maintaining your textbook standards. So actually I don't like that TH is called as T1, but anyways, I'll maintain that. And TC is equal to T2. And also QH is equal to Q1 and QC is equal to Q2. It's kind of confusing for me, but I'll just go with the flow of the books. So step, you have the expression for efficiency. Let's start with the obvious. Let's write the expression for efficiency. So efficiency is given by net work done per cycle. This entire expression divided with heat absorbed from the hot reservoir, right? So this will be W by Q1, is it not? So QH, so W by Q1. Okay. Now we know that W is QH minus QC. So if I substitute this, which is nothing but Q1 minus Q2. So if you substitute this, what do we end with? Efficiency is equal to 1 minus Q2 by Q1. Okay, so this can be the final answer. But of course, it's our tendency not to leave it over here, because what do we have control over? In a Carnot cycle, what is that we can control? We can control what kind of temperature the system is exposed to, is it not? So this is what we have control over. We have the control over what temperature should this hot reservoir be and what temperature this cold reservoir should be. So our final expression has to be something that we can control. That is the natural sense. If not, what's the point? So we basically have to express efficiency in terms of the temperature that we can handle. Temperature is what we can control. What hot reservoir, what should be the temperature? What should be the cold reservoir's temperature? That's what we can control. So our final expression should be in terms of T2 and T1. So our agenda is to relate Q2 and Q1 with, or to T2 and T1. How are these two related? To help us with that, we will make use of the set of formulas that we know. So step, we are looking at isothermal. This is step 2 actually. Isothermal's expression actually. That should be your heading. Okay. So let's start with isothermal expression. What expression do we know? We know that Q, which is equal to W, work by the system is given by nRT natural log of V final by V initial. Right guys? So this is the expression we know. So let's apply this to our first isothermal process from 1 to 2. Right? So basically if this is your graph, this part. So this part is what I'm talking about. Okay. So here your temperature is maintained at TH, which we're calling it as T1. Right? TH is T1. And your final volume is V2 and your initial volume is V1. So with all of this in mind, what do we have? Q1 is equal to NR T1 natural log of V2 by V1, I guess. Then we have, let's apply it to 3 to 4. 3 to 4. 3 to 4. So there we have Q2, right? That's your TC minus nRT2 natural log of, or let me write this actually, that will make more sense. Just substituting it will be confusing. So the temperature that we are dealing with is TC, which we call it as T2, and the volume it reaches will be V4, and the initial volume is V3. So Q2 is what we are dealing with. That's the energy coming in or going out in this case. So it will be minus nRT2 natural log of V4 by V3. So why is the negative there? So some kids get confused with this part. So why is that we have a negative sign over there? It's because of the fact that we are looking at work done on the system. Is done on the system. To take care of that, to indicate that, we have this negative sign. So basically your Q2 will be equal to nRT2, natural log of V3 by V4. Again, this is a property of your logs. So if you have a negative sign, this will flip. So I can't go to the detail, but yeah. Okay, guys. So we have the expression. So what to do with this? The natural thing for us to do is we need the ratio. So let's divide. Let's take up Q2 divided by Q1. Therefore, Q2 by Q1 will be, so we have NR that will get cancelled. T1 by T2, that's good. T2 by T1 times of natural log of V3 by V4. That is getting divided by V2 by V1 if I'm right. V2 by V1. Okay. So we are looking at Q2 by Q1 is equal to T2 by T1. We almost have the answer, but we have this big fat expression. So we need to handle this. Right, guys? If not, we already can see that in place of Q2 by Q1, if I substitute T2 by T1, we have the answer. Right? We actually know the final expression. So that is helping us. But if not, it's a natural tendency for us to try to see what this can be expressed as. Because this is also something that we can't handle. Actually, we can handle this. We can set what should be the final and initial volumes. At least V1 and V2 we can handle, not V3 and V4. But anyways, we need to simplify this as well. How do we simplify this? What to do? We'll make use of expression from adiabatic process. We are looking at adiabatic expression. So we know that TV to the power of gamma minus 1 should be a constant. This is a known fact. So this is for ideal gas. Anyways, all of this is ideal gas only. Okay, so let's apply this to process 2 to 3. So temperature at 2 will be T1, right? So I don't want to go back and forth too much, just once I'll show. We are looking at 2 to 3, adiabatic 2 to 3. So T1 to T2, and obviously V2 to V3, So T1 times of V2 gamma to the power of 1 . This is T2 times of V3 gamma minus 1. Then let's take up, apply to 4 to 1. So it is moving from T2 to T1. Volume will be from 4 to 1. So we finally have a bunch of expression that we can deal with. So we have T2 and T2 over here. Let's divide them. So let's divide above equation. And what do we end up with? T2 V4 gamma minus 1 divided by, so we need V3 actually. Let me flip it. Yeah, so we have T2 V3 gamma minus 1, and here we have T2 V4 gamma minus 1, right? Is equal to T1 V2 gamma minus 1 divided by T1 V1 gamma minus 1. Okay, T3, T2. Okay, perfect. So this and this will get cancelled, this and this will get cancelled. So let's take, so we have gamma minus 1 that we have to take care of. So taking gamma minus 1 root on both sides. So we end up with V3 by V4 is equal to V2 by V1. That's what we wanted. So since this two are equal, if I call this as 1, if we substitute this in 1, step for the simplification. Substituting above equation in 1, what do we end up with? We end up with Q2 by Q1 is equal to T2 by T1. And this, if you substitute in your efficiency, 1 minus Q2 by Q1 will be equal to 1 minus T2 by T1. That's it. Quite simple, right? All you have to do is remember adiabatic and isothermal expressions and you're done. It's actually very simple. And yeah, please see to that this negative sign you guys don't miss. People miss that I've seen. That's where they get confused. Okay, so this is your efficiency. So I have a systematic notes over here, or notes which is systematic, or notes which is neat. So I have arranged it for you guys step by step. Anyways, before I show you all of that, let me show the final expression and the conclusion. So what is the conclusion? That our efficiency depends on the cold and hot reservoirs. It's independent of the working substance. It's a maximum possible efficiency applicable only to reversible engine, of course, ideal scenario. So point is, it depends on the temperature. If the temperature, as and when the temperature difference gets higher, that is between the cold and the hot reservoir, right? So if this temperature and this temperature is pretty huge, then what happens? Efficiency gets higher and higher. Of course, T1 and T2, you can't have an infinite difference. It has to be finite. Since T1 and T2 is a finite ratio, efficiency cannot be 100%. So it's good. I mean, it's a good thing. So we are getting to see an ideal scenario in a bit realistic manner. Okay, guys. So that's how you can conclude. So you can put different values for T2 and T1 and see what is the efficiency of an ideal engine provided you keep the temperature difference about that much. So you can try putting different values. We'll also do with we'll also be handling different numericals, but people who are curious, please put and see what is the efficiency of the engine. Honestly, when I was studying, when I read through all of this, so I don't remember what exact set of values I put, but yeah, efficiency calculation is, I was curious about things. Efficiency is something you are curious about, if you are, you are. Okay, anyways, all that apart. So we are looking at this derivation, my written form. If you guys want to write this, you can. Right, and I'll show this as well.